Okay, I think it's 11 and we should get started. All right. So if you wish or if you want, you can turn on your camera because in that way I don't seem too lonely here. All right. So let's continue our topic. So last class we introduced the some basics about this class, right? So uh, basically it's the systems that we're going to deal with. So this class we're going to talk about the basic chemical concepts, okay? Because as we have shown, the environmental engineering is basically the applied science, right? Applied science that we get from the environmental science. And for a lot of these environmental science, we're dealing with chemical systems. If you recall, we talked about the MTBE, right? So uh, that's the chemical that caused quite a lot of troubles because originally we were thinking it's going to protect the air, right? It turns out that it's polluting the water because it has some special chemical properties. For example, it's toxic, it's recalcitrant, very stable in the water streams. So that's why we're going to use quite a lot of chemistry knowledge in our class, or at least when we're talking about the water treatment and wastewater treatment. In air pollution, maybe not that much, okay? So for this class, so as we have mentioned in our class, we're going to use a Davis and Maston, the third edition of the textbook, right? So the corresponding contents are in chapter 2, page 32 to 43, right? So please try to use the um, um, use the time of the class to read these pages, all right? So if we do a quick recap of our last class, we mainly talked about the major topics in the environmental engineering, right? So it's nothing but the pollution problems in different phase or different states of the matter. So we talk about the drinking water treatment or the water treatment. We talk about the wastewater treatment, which is coming from the discharged water from industry, households, or the storm water, right? We're going to talk about the air pollution control, right? It's basically these pollutants existing in the gas phase. And also the solid waste management is more talking about the landfill and so on. Okay, so also went over the history of the environmental engineering a little bit. So you can see that a lot of these problems came with the industrial revolution, right? So basically the human activities are polluting the water system and also the air, right? So we have to design engineering systems to deal with these problems. So we missed one part in our last class, which is an example of how the environmental engineering actually connects the environmental science to the general public. So if you happen to have an iPhone and then just turn to the page of the weather, right? So normally you can see this bar here, right? So at the top you can see the temperatures, right? And then further lower there is going to show the air quality index. Okay, so the index is showing a very nice bar, color bar. So, but I'm not sure if you have wondered what these color mean. So basically, the air quality index is created by the Environmental Protection Agency to help the general public to more easily comprehend what is going on with the air quality. Okay, so it is generally in the range of 0 to 500. The lower the score, the better the air quality. Okay, so generally, let's say if it's within 10 to 50, it's in good air quality, right? So yesterday in Rolla, that was 31, so which make it as the good air quality. So if the air becomes more polluted, then the color will become darker and darker. So if it's above 300, then it's going to become hazardous. Okay, but how do we define or how do we get these air quality index numbers? So we get it by measuring the concentration of the air pollutants. Okay, so this involves some more precise instruments to measure the concentration, either the mass or the number concentration of these air pollutants. So for example, it involves the PM. Normally, the PM stands for particulate matter. particulate matter, which is a very important species of air pollutants in the atmosphere, right? So people also measure nitrogen dioxide, ozone, carbon monoxide, sulfur dioxide, ammonium, lead. So these are very important air pollutants, and we use these as indicators for the air quality. Okay, so in each category of the air quality index, let's say in the green bar here, you can see that all of these air pollutants has to be within certain range, certain concentration, right? So it's basically a microgram per meter cube, uh, right? So for all of these air pollutants. So what if one pollutant, for example, ozone, skyrocketed and then end up being in this range? Okay, so the AQI is decided by the most polluted air pollutant. So even if all the other air pollutants are in the good condition, if we have an air pollutant that's in this range, then it's going to categorize as the very polluted condition. Okay, so basically, I'm trying to use this example to show how the engineers try to connect what they measure from a monitor to the general public, because we have to do this um, uh, when we design our systems, right? Or design either the real treatment system or some knowledge system to better connect to the general public, okay? So as I said, this class, we're going to talk about the basic chemical concepts. I believe for most of these concepts, you have learned that either in your high school or in your freshman year chemistry class. So what I'm trying to do is just trying to, let's say, give you a recap or just kinds of wake you up from all of these knowledges. I know that for quite many civil engineering students, this might be quite challenging for you guys because you haven't learned chemistry for a long time. So we're going to start from the basics. But if you feel that any of the comment is too quick, just send a chat, right? Or you can shout out. You can just unmute yourself, right? So if we talk about the chemistry, then everything starts from an atom, right? Although we know that atom can get further divided into smaller parts, but what eventually decides the chemical property is the atom, right? And then if we take a picture of the atom, then what we know is that the atom is composed of a nucleus, right? The nucleus is basically a cluster of protons and neutrons, right? So the protons will carry a positive charge, the neutrons doesn't have any charge on it. And then at the same time, there are a bunch of electrons circulating around these nucleus here, okay? So what decides an atom to be a certain type of element is the atomic number, okay? So the atomic number is basically the number of the protons in this atom. So for example, if we're talking about carbon, right? So we know that carbon has 6 protons, right? Therefore, the atomic number of carbon is 6. So for oxygen, it has 8 uh, protons. So the atomic number of oxygen is 8, all right? So what is the use of the neutrons? So here I'm trying to be quite harsh on it, but neutrons are kinds of useless, except that it increases the weight of an atom, right? So you will also hear people talking about the mass number. So the mass number is just the summation of the proton number and the neutron number. So for example, if we know that for the general form of the carbon, it's composed of basically 6 protons plus 6 neutrons, right? So in that case, the mass number of carbon will be equal to 12, all right? So in this class, we're going to deal with the atomic weight or the molecular weight quite a lot. Okay, so the atomic weight and the molecular weight are quite different from the mass number because the mass number is always an integer. All right, so we refer this mass number as when we're mainly dealing with one type of element, one type of atom, right? But when we're talking about the atomic weight, we have to consider all the isotopes. So again, I'm giving the example of carbon. So we know that the carbon has a atomic number of 6, right? We introduced here. And then when we try to find the mass number, we know that for most of the carbon in the Earth, right, or in the universe, it's mainly composed of, they're going to mainly have a mass number of 12, okay? So it's almost 99% of them has 6 protons and 6 neutrons, okay? But there's also around 1.1% that has 6 protons and 7 neutrons, okay? So we mentioned that what determines an atom to be an atom is the atomic number, which is the proton number, right? So what this means is that if we consider the different forms of carbon, then they're going to have a atomic weight that is not 12 or not 13. So under this situation, we need to do a weighted average. We need to basically calculate what is the average weight of the carbon in the entire system, right? So here, I'm going to give a quick quiz for our first, basically this is our first quiz question, right? Let's do a quick calculation. I hope that most of you guys are familiar with this concept here. Okay, 10 more seconds. All right, we'll stop here. And I'm going to share the result. All right, so most of you guys are correct. The answer should be 12.011, okay? So as I said, when we calculate the atomic weight or the molecular weight, we have to consider all the forms of isotopes, right? So we know that most of them is composed of the carbon that has exactly 12 of the mass number, but there's also a small fraction that has a mass number of 13. So if you do a weighted average, then the atomic weight, let's say, if you write out MC, is going to be 12 multiplied by 0.898 plus 13 multiplied by 0.011. Okay, so if you have a calculator, then you can find that this number is 12.011. So basically, whenever we talk about weight, then we need to consider the isotopes. We need to do a weighted average. Okay, so that's why we're getting this number here. So if you look at these 4 options, right, definitely it's not going to be 12, it's not going to be 13, right? And because most of most of the carbon has a mass number of 12, right? So the final answer should be somewhat close to 12. So it's a 12.011 here, all right? So similarly for compounds, let's say the calcium carbonate, right? If you want to calculate the atomic weight, or I should say the molecular weight, right? If we want to calculate the molecular weight of the calcium carbonate, then we need to find the atomic weight of the calcium, atomic weight of the carbon and oxygen, and then list out this equation here, right? And you can find out that the final answer is 100.083, 8086, okay? So I have to say that for most of the calculation in this class, we don't need to be this precise because we're dealing with engineering systems, right? So even if we consider the isotopes, it's probably at maximum will contribute to 1% of the final answer, which is kind of negligible in engineering designs, okay? So then you may wonder, where do we find these exact numbers, right? So although we're not going to use that for a lot of the calculations, but there's no way we should calculate this every time uh, when we calculate the atomic weight, right? There's no way we can find their isotope distributions. So we're going to refer to the periodic table. So I think you're probably very familiar with this table here. So the periodic table of the elements is arranging all of the elements on the Earth based on their atomic number, right? Based on the proton number here. So for example, it starts with the hydrogen, right? Has one proton number. And then the second one is the helium, right? And then lithium, beryllium, boron, and so on. Okay, so you arrange it from the left to right, the atomic number or the proton number is going to increase. Okay, so basically for each element here, let's say if we zoom into carbon, so normally you can find a 6 in here. So the 6 is the atomic number, right? The number of protons inside. So it has the name and also it has this atomic weight, okay? So in this table here, you can find what is the actual weight by considering all of the isotopes in there. So I'm hoping that with this table here, you should be able to identify which element we're talking about in the future, all right? But in this class, what we're trying to know is the general trend. So what is the feature of the elements in this table, okay? So in general, if you go from the left to the right, then the electron affinity is going to increase. So what we mean by electron affinity is basically um, basically how much this element wants to grab a electron from other elements, right? So the higher the electron affinity, it means that it prefers to take electrons from other elements, right? So this is quite easy to understand because if we talk about oxygen or fluorine, they can really take a lot of electrons from other elements, right? So basically, if you look at the first column here, right, you have all of these metal here. So the metal is very easy to give out electrons, and that's why metals are conductive because they have so many excess electrons. So basically, if you look from the left to the right, then the electron affinity is going to increase. And also for the, let's say for the last column here, if we're talking about this column or this column. So if you go from the bottom to the up, the electron affinity will also increase. This is mainly because for these smaller atoms, they have a more stable structure inside the nucleus, right? They can pose a stronger force to the electrons outside. So basically, they can attract more electrons to them and create a higher electron affinity, right? So there's also a general trend that if you go from the top to the bottom, then the atomic radius is going to increase. So this is also quite easy to understand. This is mainly because for hydrogen here, it just have one electron, right? And one electron in one single layer, right? And for these atoms, they have multiple layers of electrons or multiple trajectories. So that's going to increase the diameter or increase the radius of these elements, okay? So there's a major trend also that I want to point out is that if you go from the top right to the bottom left, then the metallic character is going to increase, right? So if you look again in this periodic table, if you go from here to here, then the elements are becoming more and more metallic, right? For example, the rubidium, cesium, right? So they are very metallic. They can even react with water, highly reactive. They want to give up their electrons so much, right? And if you go back in this direction, then it's going to become more and more non-metallic. So you cannot find any metals in this corner here, right? So this is what I'm trying to say here. So here, until now, what we're talking about is single element, right, or single atom. But we know that for most of the substance on Earth, it's not made of pure substance. It's not made of a pure atom, right? You may say that for oxygen, nitrogen, let's say hydrogen, they may be pure substance. But we know that for at least for these species, they just occupy a very tiny fraction. So what we're dealing with most of the time, water, right? Let's say there are rocks, Rocks is mainly composed of calcium carbonate, right? And then in the air, there's carbon dioxide, let's say pollutants, sulfur dioxide, okay? So these are molecules, right? And to talk about molecules, we need to first know what is making up these stable structures, okay? So what is combining all of these elements into stable structures? So this has something to do with the electron affinity, okay? So what people are trying to show is this table of the electron negativity. So you can refer this parameter as a indicator of the electron affinity. So basically, the higher the electron affinity, the larger the electron negativity, okay? So you can refer to this periodic table here. So what you can find is that if you go from left to right, so as we know, the electron affinity will become larger, right? So that's why this electron negativity will have a higher value here. And similarly, if you go from the top to the bottom, the electron affinity will become lower. So that's why for these number here, they're going to decrease, right? So now let's imagine what's going to happen, right? So for example, if we're talking about, let's say sodium and chloride getting together, okay? So what you can find is that first, we can write down the electronegativity. One is 0.9, one is 3. Okay, so this is a direct indicator of what is the affinity of the electrons. So a low number of the electron affinity for the sodium means that it wants to give out an electron, right? And the high number of the electron affinity for the chlorine means that it wants to accept an electron. And then it's made a deal, right? Because sodium wants to give out, chlorine wants to take, right? So this will basically transfer the electron from the sodium to chloride. And what we say is that basically in sodium chloride, they built a ionic bond. Okay, so the ionic bond is used to connect the sodium and the chloride. Okay, so the ionic bond is built up mainly because they have a large difference in the electron negativity. Okay, so basically you can calculate this number by taking the difference, which is 3.0 minus 0.9, you're going to get 2.1, okay? So this is one example. So what about oxygen? Okay, so we mentioned about there can be other compounds or there can be other molecules. So the oxygen is composed of 2 oxygen atoms. So if you write out the form of it and then also write out the number here, 3.5 and 3.5. Okay, so both of them wants to take electrons, but there's no extra electrons, unlike it's building up with the metals here, right? So if you calculate the difference in the electron negativity, similar to the sodium chloride, what you get is 3.5 minus 3.5 is equal to 0, right? So if this value is low or is close to 0, what we say that the bond between the oxygens is called the covalent bond. Okay, so this is basically different types of chemical bonds that's building these atoms into molecules. Okay, so to show this in a more direct way, let's say, let's draw the structure of the sodium and chloride again. Okay, so we know that sodium is on the first column of the periodic table, right? It has 1 extra electron in the outermost layer. And the chlorine, it needs an electron, right? So if you write out these 2 elements, you can find the electron negativity. One is 0.9, one is 3, right? So what's going to happen is that the sodium gives out this electron to the chlorine. And then what we're going to get is the positively charged sodium and the negatively charged electron, right? Because the sodium lost an electron, so it becomes positively charged. So we also have the names for these differently charged ions. So for example, the sodium or the positively charged ions is called cations. Okay, and the chlorine or the chloride ion is called the anions. Okay, so basically this is how the ionic bond is built up. And as we have said, the covalent bond is built up when the electronegativity doesn't have a difference or the difference is very low. So how do we tell the difference, or how do we decide whether a bond is covalent bond or ionic bond? So we're going to use the value that's shown in this table of the electronegativity. So the rule of thumb is that if you calculate the electronegativity difference, then if the difference is above 1.5, then we say that we build up an ionic bond, okay? And if the difference is below 1.5, let's say from 0 to 1.4, then they build a covalent bond. Okay, this is ionic bond. So now you can see why sodium chloride, we categorize them as ionic species, right? Because if you take the difference between these two, you get 2.1, which is about 1.5, right? Then the bond between them is ionic bond. And then for oxygen or hydrogen, nitrogen, since they have exactly the same electronegativity for the molecules inside, for the atoms inside. So because of that, they're a covalent bond. But within the covalent bond, we can also divide them based on the electronegativity, because we know that not all of these compounds are pure substance, right? So for example, let's talk about water, right? So water it doesn't have an ionic structure, okay? So so what happens is, excuse me, so what happens is we can calculate the electronegativity for these two elements, right? So if you refer to the table here, so hydrogen, the negativity is 2.1, oxygen is 3.5, right? So if you take the difference, that's going to be 3.5 minus 2.1, which is 1.4, okay? So 1.4 is right at the boundary, right at the edge of the covalent bond and ionic bond, okay? So what we're going to say is that the water is made of covalent bond, or the bond between the hydrogen and the oxygen is covalent bond. But what we're going to say is that they are not nonpolar. So basically this bond is polar covalent bond, okay? What that means is the oxygen, and the oxygen tends to grab this electron from the hydrogen, but it's not completely transferred from the hydrogen to the oxygen, okay? So the water here, or the oxygen here, tends to have somewhat a negative charge, but it's not a pure negative charge, okay? So this is how we can divide the bonds between different atoms. So further to categorize these compounds, whether it's ionic compounds or the covalent compounds, right? So to sum up here, I'm going to use this slides to just to quickly go over the contents. So basically for the ionic species, or if there's an ionic bond, then we can divide those elements into cations or anions, right? The cations are positively charged ions. For example, the sodium in sodium chloride, okay? So if there's hydrogen fluoride, you can find out that actually this is the bond between the hydrogen and fluorine is also a ionic bond. So in that case, the hydrogen here is also a cation, okay? So there can be calcium ion, can be magnesium ion. So most of the metals, they tend to form cations. So there can also be anions. So for example, the chloride ion is one of them. But these ions they actually don't restrict to single elements. So there can be clusters of elements. For example, for this cluster, what we call them is the sulfate ion. So basically The sulfur is surrounded by full oxygen, forming a pretty stable structure here. And also they tend to carry 2 extra ions here. Okay, so we also call them as the anions. Okay, so for the ionic bond, it's basically based on the calculation of the electron negativity, right? So if the electron negativity is large enough, then what it means is that anions are going to take all the electrons from the cations, right, and to form those structures. And the examples can be sodium chloride, calcium sulfate, and so on. So the covalent bond is built up when there's no complete transfer of the electrons, right? So the elements are still partly sharing their electrons, right? So examples can be methane, hydrogen, water, right? So we mentioned about the polar covalent bond. So these are categorized based on their electronegativity calculation as well. So basically, if the difference in the electronegativity is between 0.3 to 1.4, right, then those will be categorized as the polar covalent bonds. So other than these bonds here, let's say the ionic bond or covalent bond, you can see that all of these bonds involve the movement of the electrons, right? So there can be the complete movement or sharing of the electrons. So there can be also interactions that doesn't involve any electrons. So these interactions are categorized as the van der Waals forces. So you can think of it as the direct force basically between one cluster and another cluster. And this force is not dependent on the electrons. It's just a general force between some cluster, let's say some molecules or atoms. So an example can be the mercury ion attracting n number of ammonia and then form this compound here, okay? And there's no change or no transfer of the electrons. And that's why generally for this bond here or this force here, it's also very weak. It's very easy to break it apart and then basically reverse this reaction here, okay? So here we basically talk about different types of bonds, talk about different types of compounds, right? But what are the processes that create these bonds? You know that from the birth of the universe, we just get these elements, right? But how these elements form compounds, it is actually because of the reactions, okay? So unfortunately, we have to go through a lot of these reaction processes. So if you feel that we're going through too quickly, just let me know, okay? So regarding the chemical reactions, there are generally 4 types of them, okay? And we're mainly dealing with 3 types of them in our class, okay? So one type or one major type is the precipitation dissolution reaction. So in these reactions, a major feature is that it's going to form solids, okay? So whenever a reaction can form solids, then this reaction can happen and almost happen irreversibly, okay? So one very good example in the environmental engineering or the water treatment is this reaction here. So people rely on this reaction for a lot of the drinking water treatment, okay? So I guess most of us probably have seen this before, right? What I'm showing in this picture. So sometimes you can see that there are some white residues on your faucet or on your bathtub, right? So what we also call them are scales, right? So basically their major composition is the calcium carbonate or magnesium carbonate. So most of them are calcium carbonate. So the reason why we have these scales in our home is that in our drinking water, there are quite many calcium ions. Okay, and most of these calcium ions are existing in the form of the calcium bicarbonate. So they have this type of chemical composition. So the chemical property for this calcium bicarbonate is that it's very easy to break up right? So if you have a high temperature, let's say if you pour your drinking water or tap water into a kettle and then heat it up, okay? So if you heat it up, then they're going to break down into calcium carbonate, water, and calcium carbon dioxide. Okay, so if you heat it up. So we know that the calcium carbonate is basically rock, right? It's very fine size of the rock. So what this is showing is that if you boil water, you're going to generate these tiny rocks, right? Or these white residues in here. Okay, so we don't want these scales in the drinking water. I'm not sure if you have tried the faucet in the Butler Carlton Hall. I sit in the on the second floor. There's a drinking water faucet. I think right now they stop it, but before, whenever I take some water from there, I can see these white particles, or these white solids suspending in the water. So actually, those are the scales. Okay, so the reason why we see a lot of that in our building, or more generally in Rolla, is that we take a lot of our drinking water from the wells, from deep wells. Okay, so if you take the drinking water from rivers or from lakes, normally the concentration of these calcium bicarbonate or calcium ions are quite low. But if you take the drinking water from the underground water, then these concentrations will be pretty high. Okay, so definitely, I believe that the drinking water facility in Rolla tried their best to remove these ions, but in my perspective, I think they haven't done enough work yet. Okay, so actually, the way they did it is by using this reaction. Okay, so what happens is they're going to introduce calcium hydroxide into the water. So they collect calcium hydroxide by, again, by rocks, okay? So the rocks are mainly composed of the calcium carbonate. They can bake it, generally thousands of Celsius degrees, to form calcium oxide and carbon dioxide, right? And then this calcium oxide, you can just submerge into water. So basically with water, let me see, let me rearrange this place a little bit. Okay, so what happens is that by baking the calcium carbonate, you can get calcium oxide and carbon dioxide. And then by adding calcium oxide into water, you can get calcium hydroxide. Okay, so what happens is that they can produce these calcium hydroxide and then add them into the drinking water. Okay, so basically through this chemical reaction, what you're going to get is the calcium carbonate solids. Okay, so the way it happens is that they're going to first extract the underground water. So generally, the underground water is quite clean, except that they have high concentration of these calcium ions. And then they're going to introduce the water into a reactor, and then start to introduce this calcium hydroxide into the water. So because of this precipitation dissolution reaction, you're going to start to see solids are going to precipitate. So in this way, you can basically remove these calcium ion from the underground water and then send it into, let's say, the tap and then into different households. And in water treatment, or the drinking water treatment, we call this process as the softening. Okay, so clearly this has to be a well-engineered systems, a well-engineered system. So for example, if we cannot control the molar ratio or control the amount of these chemicals really well, let's say if we know what is the concentration of the calcium bicarbonate in our water, and then when we happen to dump in, let's say 4 times of the calcium hydroxide that's required by this reaction, then what we're going to do, the result is that we're actually creating more problems of the calcium ions, right? So we have to let them react based on their correct ratios, or based on their stoichiometry. So that's the importance of balancing the chemical reactions. And we're going to talk about that in our next slide. Okay. So this is the precipitation dissolution reaction in drinking water treatment system. So similarly, we can apply them into the air pollution control, okay? So the system we're talking about is the sulfur dioxide removal. So sulfur dioxide is a very important or very damaging air pollutant. So it's causing the acid rain. And also at the same time, if human breathes them in, it's going to cause allergies or some damage to the lung or the respiratory system. So because of that, there's a strict requirement for the sulfur dioxide emission. And most of these sulfur dioxide are emitted from coal-fired power plants because the coal has a lot of sulfur inside. So to deal with this problem, people created a system called the sulfur dioxide scrubber. Okay, so you can basically think of it as um, let's say a shower, a water shower for the sulfur dioxide. Okay, so similar to the water treatment, we create a reactor that's meant for the gas species. So what happens is we're going to introduce most of the polluted gas into the reactor, right? They're in the gas phase. And at the same time, you have the spray nozzles that sprays down solutions. Okay, so this is literally a shower for the sulfur dioxide. Okay, so for these water droplets, what people introduce in them is again the calcium hydroxide. So basically you have a feed and then introduce them into the pipes and then you have these water dripping down, okay? So what happens is that the sulfur dioxide is going to react with the um, calcium hydroxide, and at the same time you have oxygen in the flue gas. So what's going to happen is that first the calcium is going to react with the sulfur dioxide to form calcium sulfite, and then they're getting oxidized by the oxygen to form calcium sulfate. So calcium sulfate is quite insoluble in water. So the result is that while the water is dripping down, at the bottom you have a kind of a liquid reservoir, right? And then because of these solids, then at the bottom, basically it's going to be mainly calcium sulfate. So since it's also at the bottom, it's easier for us to extract them from the reactor. And then further, actually people use a lot of these calcium sulfate or gypsum for construction, actually. So again, you can see we use these precipitation dissolution reaction to deal with the air pollution problem, right? Either the water treatment or the air pollution control. So there can be other solids in the chemical reaction. So here I'm mainly using the calcium carbonate or calcium sulfate, but barium sulfate is an example, aluminum hydroxide, magnesium hydroxide, iron hydroxide, and so on. So all of these are insoluble. So we can use these chemical properties to generate reactions that remove certain type of pollutants, either in water or in the air. So another category of the chemical reaction is the acid-base reaction. So this is quite straightforward, right? So if you realize that the water is too acidic, then you can add in base, right? So people also use this method quite a lot in wastewater treatment because so a lot of the wastewater processing or wastewater treatment is going to change the pH of the water. So it's either becoming too acidic or too basic. So under that situation, you need to add in either acid or base into the water to basically neutralize these extra acid or base to generate water, right? So before you discharge it into the environment. So another major type of the reaction is the oxidation reduction reactions. So people also call this as the redox reaction. So basically it's the reduction oxidation reaction, okay? So we use these reactions quite a lot when we're dealing with the organic pollutants in the water. So since we used Rolla, for example, let's also use St. Louis as for another example. Okay, so St. Louis use or get their drinking water from the Mississippi River. Okay, so we know that for river water, for a lot of time, it contains quite many pollutants or quite many, or we shouldn't say trash inside, but definitely the water quality in the river is not good. Okay, maybe not as bad as this one, but we know that whenever there's a rainfall or a storm, a lot of the, let's say the leaves or some chemicals from the farmlands, they're going to get discharged into the water. Okay, so a lot of them are organic and they're toxic to human. Okay, so these organics are mainly composed of carbon, hydrogen, oxygen, right? So what is the easier way to deal with these organics? So actually people use bacteria or microbes because these bacteria live on organics to sustain themselves, right? So for water treatment, we can use these to reduce the organics or the amount of the organics and to purify the water, okay? So this is an example of the oxidation reduction reaction. So another type can be the complexation reaction. So this is the formation of compound that has the interaction of the van der Waals force. As we mentioned, we're not going to deal with this type of reaction in this class. Okay. So since we talk about the reactions, as I've introduced, we need to balance them because in engineering systems, we want to make sure that at least the amount we input into the treatment system is working, right? We're not creating more problems. So that explains why we need to do it, because we can accurately design the engineering systems. So for example, let's take the water softening as an example again, okay? So as we mentioned, the major goal is to try to reduce the calcium bicarbonate in water. And the procedure is that actually we add in more calcium ions into the water. And this is uh, mainly relying on the hydroxide ions to react with the bicarbonate ions and to form these solids. Okay. So now let's think of this chemical process. So what happens is that we have this reactor here, and then the water is being introduced into this tank here, and then this is exit. And at the same time, we add in this calcium hydroxide. So because there's sedimentation, right, we have solids at the bottom. But the thing is that we cannot keep these solids infinitely long because they're going to build up, right? And you don't want to let these solids to fill the entire tank before you clean up the tank and then, uh, um, let's say, and then make it back to work again. So what happens is that we want to continuously extract these solids at the bottom, right, at the correct rate. Okay, so that will involve the calculation of how much of the calcium carbonate is going to form here. So then it came with a question how to balance this reaction, because clearly the calcium ion is not conserved on the left-hand side and right-hand side. Okay, so I think probably we're getting to the end of this class, but the balancing is just adding the correct number before these chemical compounds so that they will make sense in their, let's say, the amount in their reaction, right? So if you look at this reaction, so basically you're going to form two number of calcium carbonate and two number of water, okay? So similarly, we can balance other types of reactions. And I think you can probably try to balance these reactions off the class. So we're going to continue our discussion in our next class, all right? So that's it for this class, and I'll see you on Wednesday.
I'll see you. Thank you.
Yep, thank you.